Have you ever wondered how your smartphone charges wirelessly or how an electric toothbrush charges without a direct plug? These marvels of modern technology and so many more are possible thanks to a principle known as electromagnetic induction. It's a concept that powers our lives, often without us even realizing it. From electric cars to induction cooktops, it's an unseen force that facilitates convenience and innovation. So buckle up, because today you will unravel the mystery behind this fascinating phenomenon. To comprehend electromagnetic induction, first you need to grasp the concept of electromagnetism. Simply put, electromagnetism is a branch of physics that studies the relationship between electricity and magnetism. It's a fundamental force that governs how charged particles interact with each other and with magnetic fields. Let's break it down a bit further. You see, when an electric current flows through a wire, it creates a magnetic field around that wire. This is the principle behind electromagnets and electric motors. But the really fascinating part of this is that the process can also work in reverse. That's right. A moving magnetic field can induce an electric current in a wire. This is known as electromagnetic induction. And what's the driving force behind this? It's all down to a property called flux. Flux, in this context, is a measure of how much magnetic field is passing through a given area. As the magnetic field changes, so does the flux. And this change in flux is what induces an electric current. So in essence, electromagnetism is all about the interplay between electricity and magnetism. It's a two-way street where electric currents generate magnetic fields, and changing magnetic fields induce electric currents. And it is this interplay between electricity and magnetism that leads us to electromagnetic induction. So, what exactly is electromagnetic induction? Well, let's dive right into it. Imagine you're at a concert and the music is so loud you can feel the vibrations in your chest. That's a bit like electromagnetic induction. In this scenario, the booming bass is like a changing magnetic field, and your chest is like a conductor. The vibrations you feel, that's akin to the electric current that's induced in the conductor. Electromagnetic induction, in its simplest form, is the process of generating electricity through the use of magnetism. But how does this happen? Think of a magnetic field as a sea with waves flowing through it. Now let's introduce a boat, which represents our conductor. If the sea is calm, the boat remains still. But if the waves start rolling, the boat begins to move. Similarly, if the magnetic field around a conductor is static, there's no electric current. But when the magnetic field changes, it stirs up an electric current in the conductor, just like the waves rocking the boat. This all happens due to the magic of electromagnetic induction. The changing magnetic field creates a force that pushes the electric charges in the conductor around, making them flow. This flow of electric charges is what we know as electric current. But here's the catch: the change has to be dynamic. If the magnetic field changes once and then stays the same, the electric current will cease. It's like if the waves rocked the boat once and then stopped, the boat would eventually become still again. So, for a continuous current, we need a continuously changing magnetic field. And that's the beauty of it all. It's a dance. The magnetic field and the conductor constantly interacting, constantly changing, and in the process, creating electricity. In essence, electromagnetic induction is the process of generating electricity using magnetism. It's a fascinating phenomenon that powers our world, from the smallest electronic devices to the largest power plants. So, the next time you switch on a light or charge your phone, remember you're witnessing the magic of electromagnetic induction. Scene script: two laws govern electromagnetic induction: Faraday's law and Lenz's law. Now let's shine a light on these two laws. Faraday's law, named after the great scientist Michael Faraday, is a cornerstone in the study of electromagnetism. It states that a change in magnetic field within a closed loop of wire induces an electromotive force, or EMF, in the wire. Simply put, if you move a magnet near a loop of wire, you'll generate electricity in that wire. The amount of induced EMF is directly proportional to the rate at which the magnetic field changes. This means if you move the magnet faster, you generate more electricity. Faraday's law is the reason we have generators and transformers, which are fundamental to the distribution of electricity. But wait, there's another piece to this puzzle. Enter Lenz's law. Named after Heinrich Lenz, this law is a bit like the universe's way of keeping things in balance. Lenz's law states that the induced EMF will always work to oppose the change that produced it. In our magnet and wire loop example, if you move the magnet towards the loop, the induced current will create its own magnetic field to push the magnet away. If you move the magnet away, the induced current's magnetic field will try to pull it back. It's like the universe saying, "Hold on, not so fast, you can't have something for nothing." Together, Faraday's and Lenz's laws describe the principles of electromagnetic induction. They tell us how we can generate electricity from magnets and how the universe keeps this process in check. It's a dance of forces and fields, and these two laws are the choreographers. They're not just abstract scientific principles either. Every time you charge your phone or when the lights in your home flick on, you're witnessing the effects of electromagnetic induction. These laws aren't just rules written in some old textbook. They're happening all around us, all the time. These laws lay the groundwork for the practical applications of electromagnetic induction. Electromagnetic induction isn't just a cool scientific concept, but it has numerous practical applications. It's the invisible force that powers your everyday life, from the moment you wake up to the time you go to bed. Let's dive into some of these applications to see how electromagnetic induction is at work. First, let's talk about transformers. No, not the shape-shifting robots, but the devices that step up or step down the voltage in an electrical circuit. Transformers work on the principle of electromagnetic induction. They consist of two coils of wire known as the primary and secondary coils. When an alternating current flows through the primary coil, it creates a changing magnetic field. This changing magnetic field then induces a voltage in the secondary coil. By varying the number of turns in the primary and secondary coils, we can control the output voltage, stepping it up or down as needed. Next, let's move on to electric generators. These are the devices that convert mechanical energy into electrical energy, again using the principle of electromagnetic induction. In a simple generator, a coil of wire rotates in a magnetic field. As the coil rotates, the magnetic field through the coil changes, inducing a voltage in the coil. This induced voltage drives an electric current, and voila, we have electricity. Now let's turn to something you might have on your desk or nightstand right now, a wireless charging device. These devices also use electromagnetic induction to transfer energy. When current flows through a coil in the charging base, it creates a magnetic field. Place your phone or other device on the base, and this magnetic field induces a current in a coil inside your device. This current then charges the battery, all without a single wire connecting the base to your device. Finally, let's not forget about induction cooktops. These modern marvels heat your pots and pans without any direct contact with a flame or heating element. Instead, they use a coil beneath the cooktop surface to create a magnetic field. This field induces electric currents in your pot or pan, which generate heat due to the resistance of the material. And just like that, your water boils, your soup simmers, and your dinner cooks, all thanks to electromagnetic induction. As you can see, electromagnetic induction powers our modern world in more ways than you might have imagined. Let's quickly recap what we have learned today. We started off with a provocative question and then plunged into the fascinating world of electromagnetism. We discovered how electric currents and magnetic fields interact, giving rise to the phenomenon we now know as electromagnetic induction. We then delved deeper into the magic of electromagnetic induction, revealing how a change in magnetic field can induce an electric current in a conductor. This is a concept that might have seemed like magic centuries ago, but today we know it as a fundamental principle of physics. We then explored Faraday's and Lenz's laws, which govern the process of electromagnetic induction. Faraday's law tells us about the amount of voltage induced, while Lenz's law helps us understand the direction of induced current. These laws are not just theoretical concepts, but are the backbone of countless technologies that permeate our daily lives. We also discussed the practical applications of electromagnetic induction. From power generation in hydroelectric dams and wind turbines to the functionality of our everyday household gadgets like electric toothbrushes and wireless charging pads. These examples show how electromagnetic induction is not just a topic of academic interest, but a principle that has immense practical significance. And that, my friends, is the power and mystery of electromagnetic induction demystified. Keep exploring and stay curious.